Every winter, millions of us experience the exact same betrayal of physics. You step onto a frozen sidewalk, and your foot shoots out from under you. We all know ice is slippery, but why it stays slick, even in the deepest freeze, is a question that has divided scientists for over a century. If you open a standard high school physics textbook, you'll likely find a clean, intuitive explanation called pressure melting or regelation. The logic follows the unique density of water. Because solid ice takes up more volume than liquid water, applying enough downward pressure, like the weight of a person, supposedly forces the structure to contract back into its denser, liquid state. You briefly melt a microscopic layer of water, slip on it, and then it refreezes once the weight is removed. It's an elegant idea that makes perfect intuitive sense, but the thermodynamic math suggests the human body is far too light for this to actually happen. This chart maps out the phase boundary between solid ice and liquid water. To drop the freezing point of water by even 1 degree Celsius, the pressure must increase by over 100 atmospheres. A 150-pound person standing in flat winter boots spreads their weight over a large surface area. The pressure they generate results in practically zero shift in the melting point. Even the razor-thin blade of an ice skate only generates about 40 atmospheres of pressure. That lowers the melting point of the ice by just 0.3 of a degree. If pressure melting were the primary mechanism, we could only skate on ice that was already hovering at 0 degrees. Yet people routinely glide on ice at -20. To bridge the gap, researchers proposed frictional heating, the idea that the kinetic energy of a sliding shoe generates enough heat to melt the surface. But that doesn't explain why your foot slips the instant you step onto black ice, while standing completely still, before any motion has occurred. If your weight can't crush the ice into a liquid, and you haven't moved yet to heat it up, the ice must have a built-in mechanism for slipperiness. In 1842, Michael Faraday pressed 2 dry, freezing ice cubes together and found they instantly fused into a single block. He deduced the cubes locked together because they were coated in a microscopic film of liquid water, even though the air was well below freezing. To find that water, we have to scale down to the nanoliter level and look at the chemical architecture deep inside the ice. Deep within the crystal, water molecules form a rigid hexagonal lattice, each locked by 4 strong hydrogen bonds. But at the boundary layer meeting open air, top molecules are severed from the grid above. They have only 2 or 3 bonds instead of 4. Lacking that structural framework, the surface molecules cannot maintain a rigid form. They are caught in a state of physical crisis. To maximize their stability, these exposed molecules begin breaking and reforming their remaining bonds billions of times every second. Physical chemists call this highly active state the quasi-liquid layer. Instead of a static grid, the outermost molecules become highly disordered, diffusing across the surface like unanchored rolling marbles. This natural molecular dance creates a layer 1 molecule thick, even at -38 degrees Celsius. It requires no human interaction. Ice is a continuously evolving, highly mobile interface. It is inherently slippery. The thickness of this quasi-liquid layer is dictated by the ambient temperature, growing in discrete, stepwise phases as the environment warms up. This spectrum maps the layer's thickness. At -40 degrees, the ice feels sticky, almost like concrete. At this extreme, the quasi-liquid layer is too thin to function as a lubricant. At 0 degrees, the layer becomes too thick. It turns into bulk liquid water, which creates hydrodynamic drag that slows objects down. The sweet spot for gliding is around -7 degrees Celsius. Here, the layer is precisely thick enough to act as an atomic roller bearing without causing drag. The quasi-liquid layer provides the initial, friction-free gateway that allows an object to start sliding. Once it is in motion, the heat of friction takes over to melt additional layers and sustain the glide. This same molecular scale disorder drives massive geological changes. The quasi-liquid layer forms a fluid highway underneath glaciers, a process called basal slip. This ultra-thin molecular lubrication allows millions of tons of ice to deform and glide smoothly over solid bedrock. By understanding these behaviors, materials scientists are developing hydrophobic asphalt coatings that disrupt the quasi-liquid layer, preventing winter roads from becoming slick before a car even drives on them. The act of slipping on a winter sidewalk is a consequence of the molecules at the very edge of the frozen world. They are violently breaking and forming chemical bonds, caught in a permanent dance to stabilize themselves.